So here we're going to prove the first step of the Giorgi's theorem, that is the L2 to L infinity bound on solutions of elliptic equations in divergence form with bounded measurable coefficients. All right, so in order to do this, we're going to mimic the proof that we saw in the previous video on minimal surfaces. And we're going to observe first that the inequality that we want to prove is a simple consequence of the following, that if the L2 norm of the positive part of U is smaller than some fixed delta, depending on dimension and lambda only, then in fact, U has to stay away from 1 from below in the ball of radius 1/2. So this is sort of a quantitative version of the maximum principle in that U is most of the time in some L2 sense bounded below 0. And the conclusion is that it has to stay also in the sup norm sense bounded below 1. Okay, so why is this thing enough to prove this inequality? Well, you see, first, if the L2 norm of U is smaller than some delta, then also the L2 norm of U plus is going to be less than some delta. And so we'll get already that U is less than 1 in the ball of radius 1/2. And now if you apply the same reasoning to minus U, which solves the same equation, then you'll get also that U is bounded away from -1. And in the end, U is going to be bounded in the case where the L2 norm is small. And now it's just a simple scaling argument that if U has finite L2 norm, then U divided by delta times delta divided by its L2 norm is going to satisfy this assumption, and the whole thing is going to follow by linearity. Okay, so now let's see how we're going to do this. This is again a dyadic method, so let me draw here a possible graph of the function U. And that is, pretend for now that the function is going to have values above 1, which is possible, by the way, outside the ball of radius 1/2. And here we have the level 1/2 that I'm going to draw right here. And we're going to do a dyadic decomposition on level sets of U. That is, we're going to look at what happens when U is below or above 3/4. And the same thing more generally, we're going to look at the level set 1 minus 2 to the minus k. So the interesting quantity that we want to look at is U minus 1 minus 2 to the minus k. And we take the positive part of this. And also, this is a novelty compared to the previous proof. We have to locate things in space. So we're going to take a cutoff phi k, which is equal to 1, let's say, up to the radius 1/2 plus 2 to the minus k plus 1. And then from there on, it will have a transition and go to 0 at 1/2 plus 2 to the minus k. So here is the norm of x, and phi k is a radial function. And this is the level 1. Okay, and instead of using minimality, we're going to use the equation satisfied by U. And what we're going to do is simply multiply the equation, so which I recall, which is divergence of A of x grad U equal to 0. We're going to multiply the equation by this truncated function uk times phi k squared. So let's do this at the level k plus 1 because our goal is to get again a recurrence relation between uk plus 1 and uk. So what do we get when we do this? Okay, we have that 0 is equal to the integral of A of x grad U times the gradient of uk plus 1 phi k plus 1 squared and x. Now we can expand this quantity. The first one is going to be the integral of A of x gradient u times gradient of uk plus 1 times phi k plus 1 squared. That's the first term. and plus twice the integral of a of x rad u to the k plus 1, phi k plus 1, gradient of phi k plus 1 dx. There are dot products everywhere, as you imagine. Okay, now you see what is the gradient of uk is simply going to be the gradient of u on the set where u is bigger than 1 minus 2 to the minus k, is going to be 0 elsewhere. And as a result, when you take the dot product with the gradient of u, you simply get a of x gradient of uk plus 1, dot product with gradient of uk plus 1, phi k plus 1 squared for the first term. And you can do the same for the second quantity, which is going to be, again, the same quantity, but with uk plus 1s everywhere. So these two expressions here, since the matrix A is symmetric and we have a quadratic form at hand, looks very much like the beginning of a square. And it is, in fact. It is going to be simply the integral of a of x times the gradient of phi k plus 1 times uk plus 1, dot product with the same. But if we do this, we forgot a term, which is simply the integral of a of x u to the k plus 1 squared, gradient phi k plus 1, dot product with gradient phi k plus 1. Okay? Now this quantity is something that we can estimate from below using the ellipticity, and so we get that lambda times the integral of the gradient of phi k plus 1 uk plus 1 squared is going to be less than 1 over lambda for the L infinity norm of A times, so let's see, the gradient of phi k plus 1 is going to be, if you look at the graph of phi k, of size 2 to the k, so there's going to be a 4 to the k that's going to be coming in, and some universal constant depending on dimension only. And what's left is the integral of uk plus 1 squared. And we can be a little bit more precise about this by saying that this is really integrated on the support of phi k plus 1. And this is quite convenient because on the support of phi k plus 1, since we chose a dyadic decomposition, phi k is identically equal to 1. So what we can say is now that we have a bound in terms of 4 to the k times the integral of uk phi k squared. Yes, I forgot to mention that also, obviously, uk plus 1 is going to be less than uk where we're looking. So we've come up with the following energy estimate that we're going to use again. So keep that in mind, this energy or Cacciopoli type estimate. And now instead of the isoparametric inequality that we use for minimal surfaces, we're going to use its analog for elliptic PDEs, which is the Sobolev inequality. And the Sobolev inequality states the following, that the integral of phi k plus 1 uk plus 1 to the 2 star, to the 2 over 2 star, is going to be less than a constant times the integral of gradient squared of the same quantity. And this we have seen just before that it was bounded by 4 to the k, the integral of uk phi k squared. All right, now we're close to the point. We're going to look at the L2 norm of uk phi k. Here we have a L2 star norm. So how do we link the two? Just by interpolation, by looking at the L2 norm of uk plus 1 phi k plus 1. So this is going to be less than, by Holder's inequality, the L2 star norm of the same quantity to the 2 over 2 star. And then we have the measure of the set where we're integrating, in other words, the set where uk plus 1 phi k plus 1 is positive, to the conjugate exponent, 1 minus 2 over 2 star. Okay, this is the quantity that we've just bounded above, so let me write it again. C times 4 to the k the integral of uk phi k squared, and this quantity is to the power 1, because we had a 2 over 2 star. And what about this quantity? Well, on this set, as we said, phi k is going to be equal to 1. And also, uk plus 1 being positive, we know that uk is going to be bounded below by 2 to the minus k. So we can bound by 2 to the minus k minus 1, sorry. So we can bound again this measure by 4 to the k plus 1 times the integral of uk phi k squared. And this whole thing to the power 1 minus 2 over 2 star, which is just 2 over n. So if we combine these two things together, we get 4 to the k times the integral of uk phi k squared, and this whole quantity to the power 1 plus 2 over n. And now we're done, you see, because we're in the same situation as for minimal surfaces. There is this factor here that looks bad, but since the exponent here is very large, if we assume from the start that the L2 norm is small, so if u plus on L2 of B1 is less than some delta, then the conclusion of this is that in the limit u infinity phi infinity is going to be identically equal to 0 almost everywhere in B1 half. And this means that u minus 1 plus is equal to 0 almost everywhere in B1 half, and that's what we wanted to prove.